All right, this video is going to go through the last part of notes for the bonding chapter, intermolecular forces. Then what we're going to do is grade bonding 4, and then we are going to look at like dissolves like, and then we will look at the pre-lab so that you know what you need to do for homework. So intermolecular forces, they are what make solid and liquid molecular compounds possible. First type of intermolecular force is called the London dispersion force. These are caused by momentary dipoles of constantly moving, right? So if I asked you to disperse around the room, you would move. So it's just the idea, right, that these molecules are moving. And so electrons between nonpolar molecules is when we have London dispersion forces. You'll probably want to highlight nonpolar molecules. When it comes to dipole occurs when polar molecules are attracted to each other. So these are slightly stronger than dispersion forces, and so we have to look at them as almost like there's the attraction of negative to positive, right? But it's not completely hooked like the ionic solids. They are just going to continue this pattern of negative is attracted to the positive. So here's the idea. Negative attracted to the positive, negative, positive, and so on. Hydrogen bonding is the strongest. These are intermolecular forces that are caused by an attractive force where hydrogen is bonded to F, O, and N. If you look at where F, O, and N on their periodic table, we know that fluorine is the most electronegative atom. So these three elements are very electronegative, so they have a very strong dipole. So examples would be things like HF, NH3, H2O. And it's important that you recognize, right, that when you look at the molecule, it has to be the H directly attached to F, N, and O. You can't just look at, is there an F and an H or N and H, O and H? Those two atoms have to be connected to each other. So because there are three elements, NOF, you can think of, is it strong enough, okay? So now, since I already know that it's the strongest intermolecular force, right, you want to make sure that you check for that type of intermolecular force first. So here's the idea of hydrogen bonding. The negative end is attracted to the positive. Remember, these are, right, dipole forces, but it's a stronger type of dipole force because specifically with O and the H, so HO, NHF. So now, how do I determine intermolecular forces? You always check first. So check first for hydrogen bonding. Does the molecule have HF, HO, or HN bonding? Then you're going to check for if the molecule is polar. If it's polar, dipole. If it's nonpolar, you're going to say that it's dispersion. Now, what if you have more than one type of hydrogen, or what if you have more than one type of intermolecular force? You don't write that it has all three types. What you're going to do is pick the strongest, okay? So now what we're going to do is we're going to practice. So on page 11, so now we're on page 11. We're going to look at page 11 and figure out if these molecules have hydrogen bonding, dispersion, or dipole. What I like to do, right, is I write on here, first, does it have HF, HO, HN, right? Dispersion is if I said that it's nonpolar. Dipole if it's polar. And I always check for this one first, okay? So where do I look? I look at the previous column. So let's see. This one here, does it have HF, HO, HN? No. So then now I have to decide, right, between dispersion and dipole. Because I said that this molecule is nonpolar, it's dispersion. And you can go ahead and shorten it by just writing DISP. Next one. First check, do I have HF, HO, HN? No. Next thing, is it non-polar or polar? It is polar. So because it's polar, I have dipole. Maybe, whoops. 3-4 years ago, I had a student that said, can we just shorten it dip? I'm okay with that. All right, but dipole. Now we're moving on to page 12. Same idea. So here, first check for HF, HO, HN. Then I check for dispersion and dipole. So dispersion is nonpolar, dipole, polar. Remember, for these two, I look here. For this one, I actually look at the structure. So here, do I have HF, HO, HN? No. It's nonpolar, dispersion. Over here, now, first check, does it have HO, HF, HN? No. So then I look at this column here, nonpolar, dispersion. Here, check, does it have HF, HO, HN? Has HN. HN means that it is going to be hydrogen bonding, and you can shorthand that H bonding. Next one, do I have HF, HO, HN? No. This is, we said that it was nonpolar, right? But because it's nonpolar, it is dispersion. And then the last one, right? You got to be careful, because what if I just looked at this, that it's polar, right? Then I might think it's dip, dipole. But I always have to check for HF, HO, HN. So HO is here, so that is hydrogen bonding. All right, so now what you want to do is have bonding 4 out. And before we grade it, I would like for you to complete the last column of bonding 4 worksheet. So remember, on the bonding 4 worksheet, you didn't do the last column. So go ahead and do the last column, and then when you're ready to check bonding 4, right, take out a red pen. So remember, you are going to finish up this column here. Before we grade, right, bond type, you should have put your dipoles and designated what color you used, right? But here, go ahead and fill this out on front and back, and then we're going to grade. So you can pause the video and then resume after you have finished both sides, because then now we're going to grade. It's going to be out of 82 points. Make sure you write in red. Okay, now we're going to grade this. So the available electrons aren't worth any points, but go ahead and grade. I decided to do my dipoles in this pink color. 2 points for the structure, 1 point for the dipole, no resonance, 1 point for the name of linear, 1 point for drawing it straight across, 1 point for the work here, 1 point for saying that's polar covalent. Molecule type is polar because it doesn't cancel. Dipole would be the type of intermolecular force. Next one, HF has a dipole pointing towards the right. No. Linear should be drawn linear. 1 point for 1.7, or having the work here. 1 point for same polar covalent. The overall molecule is polar, has hydrogen bonding. BeI2, this is a structure, 2 points. 1 point for dipoles, no resonance, linear. Make sure you draw it that way. Polar covalent, nonpolar, dispersion. SiS2, here you have 2 double bonded S's with the Si. This looks like CO2. No resonance. It's linear. You should draw it straight across. You should have your dipoles. Polar covalent, but it's nonpolar because these cancel. Dispersion. Here I have NF3. No resonance. Trigonopyramidal. Remember, these lone pairs need more space. Polar covalent. That's why we drew these dipoles pointing towards the F. The molecule is polar. Dipole would be the type of intermolecular force. SiBr4, you have no resonance. You can definitely draw it like this so that it is tetrahedral, or you can draw it like a plus sign. Polar covalent, that's why we drew the dipoles, but it's nonpolar because they're equal angular. Dispersion. O3, make sure you know how to do this one for the test, okay? So this one, you're going to have your lone pair on O. Yes, it has resonance. You have to draw the correct structure, the resonance structure. In this case, the arrow is worth 1 point. Draw it bent, should look bent. Now, I need you to understand something. Yesterday in the notes, I said that if you have a lone pair on the central atom, it is going to be a polar molecule as long as you have at least one dipole. Well, there's no dipoles here, so it's nonpolar dispersion. Bi3, this is the one that we saw yesterday, actually in class, BF3, okay? No resonance, trigonoplanar. Polar covalent, which means I have 3 dipoles, but they cancel because these are all equal angular. I would know this shape for the test. Know that it's nonpolar because these dipoles cancel, so dispersion. So please have your score out of 82, and then save this for the next time I see you in class. All right, last thing we have to look at is solubility. So now we are back on page 13 of the notes. Solubility has a saying that says, like dissolves like. So polar solutes dissolve in polar solvents. A polar molecule will dissolve in water. Nonpolar dissolves in nonpolar solvents. So a nonpolar molecule will dissolve in oil. So the point is that if I want to dissolve something, they have to have similar polarities. Now, what you have to know, though, is ionic would be a very polar substance, right? Because it has a positive and a negative end, so it's a very polar type of compound, but we call it ionic. But you can put it into this category here. All right, so now you're going to watch a video to help you understand solubility.
An important concept in general chemistry is the principle of like dissolves like. This means that nonpolar solutes dissolve in nonpolar solvents, while ionic and polar solutes dissolve in polar solvents. Here I have water, which is polar. Here I have hexane, which is nonpolar. I'm going to add some iodine to the water. Iodine is nonpolar, so it shouldn't dissolve, but I will warn you the water takes on a little bit of a brownish tint because iodine has a really high vapor pressure. It actually sublimes at room temperature. So you can see it just hangs out in the bottom. Again, that brown color is from the high vapor pressure of iodine. Now I'm going to add some hexane. Hexane, being a nonpolar solvent, the iodine should dissolve very easily into it. To help it mix, I'm going to take it out and shake it. You can see from the bright purple color up here that iodine has dissolved in the hexane. Here I have hexane, again, nonpolar, and I've got some copper chloride, which is ionic.
So remember, ionic is just a very extreme polar molecule.
You can see it sinks right to the bottom. When I add some water, the copper chloride should dissolve immediately into the water. Thus, we can see that the ionic compound dissolved into the polar solvent, while the nonpolar compound dissolved into the nonpolar solvent.
Now we're going to do some practice here. So here I have the molecules, and we did all these molecules except for I2 on page 12 of the notes. So we have CO2, CCl4, NH3, BF3, H2O, and then we also have I2, which is one that I said we didn't do, but we know what these are, right? We know that CO2 is nonpolar, CCl4 nonpolar, NH3 polar, BF3 nonpolar, H2O polar. And iodine, we just watched a video, that's going to be nonpolar. So will it dissolve in water? Well, what I have to know is that water is polar, oil is nonpolar. So if I have CO2, which is a nonpolar molecule, it's going to dissolve in oil, like dissolves like. CCl4 is a nonpolar molecule. It's going to dissolve in oil. NH3, polar molecule, going to dissolve in water. BF3, nonpolar molecule, dissolves in oil. H2O, polar, dissolves in a polar molecule like water, right? Like dissolves like. I2 is nonpolar. It's going to dissolve in oil. So this concludes our note. Now what we're going to do is look at what our homework is. All right, our homework is to complete the pre-lab and have it uploaded by 8 a.m. on Monday. This is important because you got to have the pre-lab done to do the lab. You're going to find the available. Draw the structure to shape, right? If it has resonance, you should be drawing all structures, connecting them with a double-sided arrow. I would encourage you to use page 4 of the notes to make sure you have all of these things included in your structures, right? Bond type, right? You're going to show me the work. Even if it ends up being 0, right? You have to, like here, O2 and O2. You got to figure out the electronegativity values, which is 3.44, 3.44. Subtract those, get 0, nonpolar covalent. Then tell me what type of intermolecular forces they have, okay? I do want you to draw dipoles in a different color. Okay, so that is front and back. Another thing you need to do is read over this. Please read over this to make sure you know what colors you're going to need, all right? And then it would help, right, if you put these hints into your pre-lab. So when you use SO3, use black for sulfur. So I would definitely, right over here, SO3, use black. 4 holes for sulfur. Okay, so once again, this is due 8 a.m. on Monday.